So we've got a keynote address to start off with, and then heading straight into the plenary session. And so it's my great pleasure to introduce John Hare. I'm not sure he needs terribly many introductions, but John is a structural engineer and chief executive of Holmes Group. He's worked in New Zealand, the UK, and the US, where he established Holmes' office in San Francisco in the early 2000s. And he's been based back in Christchurch since 2006. John's a life member of both CSOC and the New Zealand Earthquake Engineering Society, and in his own words, both of which he has subjected his rents to over many years. John's going to build on some of the themes that were discussed this morning around the way in which you use engineering models, a talk I'm really looking forward to. So with no further ado, I'll hand over to John.
Right. Okay, thank you, Hamish. Looking around, this is a large group of people to give this address to, and I must admit I thought when I put it forward it would be worthy of a 10-minute or so section somewhere, so it's been expanded to 40 minutes. Conscious this is the after-lunch session. If anyone feels the need to have a bit of a snooze at some point, just keep it quiet and carry on. So I think it's always good to start a talk with a quote from someone much wiser than me, and so George Box here is, I think, credited with being the father of TQM and various other things, very smart man, but I think this quote here is probably the most relevant thing, and if you take nothing else from this talk, this would be what you should take away from it. So, all models are wrong, but some are useful, and that's really the guiding theme for this talk. I'm thankful for Carl this morning, wherever he is, for sort of giving me the excuse here to say that it was, in order to look forward, you've got to look backward. And so there were certainly three things, I think, looking backward that really have prompted this talk. One was, I hate to say it, but the terrible amount of time I've spent over the last number of years looking at various things that have gone wrong. And some of them were external projects and things which have gone wrong, and those are always the slightly better ones to learn from because they don't involve so much individual pain. Others, I'd have to say, unfortunately, were the ones that were internal, and those are a little more painful. But nevertheless, as we like to say, they're not failures, they're learning experiences, and so hopefully we've learned something from them. The second one was that at the ripe old age of about 50-something, I suffered the unusual experience of being given some assignments from a former lecturer. And I thought, hadn't I been away from that long enough that I still have to do that stuff? But anyway, David Elms tracked me down and wanted to talk to me about a few things related to work that he was doing, looking at building failures. And some of that, he gave me some reading assignments, which I duly went through and discovered there was quite a lot of interesting stuff in there. And so, unashamedly, I'll say a lot of what I'm about to talk about is basically plagiarism. But anyway, I think someone said the best work often is. And the third thing was, really looking back a long way, a reflection that in about 1985, I think, there were three bright, shiny new things appeared in the Holmes office. Not all that bright and shiny because I was one of them, but this was one that appeared at that same time. And so the original IBM PC-AT, I think with a 286 processor, 64K of RAM, and 2 megabyte hard drive. It was the greatest thing. And but looking back, it sort of caused me to reflect a little bit. I was probably in that happy sort of cusp period between when getting trained in totally in hand methods of doing everything. Paul referred to some of that arcane stuff this morning. I won't try and use any of the terminology again, but it was all good stuff, and that was how we took it for granted that we do things. And then these came along and things changed. The beauty of 64K of RAM and 2 megabytes of hard drive is that you can do very little with it. But it made you think very hard about what you did do. And so you'd spend the time to reflect on exactly what you needed to model, what was really critical, and how you'd therefore get what you were looking for. And I think that's something which, at risk of sounding like a bit of a Luddite, has been lost somewhere over the years. And so a lot of this talk is about how we might think of some of that. So, what's a model? Well, most budding young engineers of a certain age probably played with this stuff as kids. And so back in the day in Meccano, you could construct all sorts of delightful engineering type structures, maybe from plans, or maybe from your own head. So it was a lot of fun, and I think a lot of people still talk about Meccano somewhat glowingly, even, I suspect, if they haven't ever seen it before. And obviously that moved forward, and these days it's Lego, and that's probably even a bit out of date. There's more things still. But we start thinking of models at a very early age, even if we don't really think about it very much at all. Scroll forward a little bit. What's an engineering model? Well, I think it starts at this point. I've often said to people the best time you spend on a project is staring out the window before you even put pencil to paper, thinking about what it is that you're doing. And so it's that concept that you develop, that picture in your mind about what something is, better still, how it will behave when we start subjecting it to actions that we think it may be subjected to. And then maybe that translates forward into what you see on the computer screen and how you start analysing things. And better still, if you're lucky, it eventually gets built. And so, in fact, the sketch you see on the left and what you see on the right are the same thing. And lo and behold, it all happens. And so what I'm really want to talk about here is perhaps the importance of that early model, the first thing that comes into your mind as being the most critical model of all. One of the things that David Elms came up with, that he showed to me, was some work that he was doing with an international colleague, Colin Brown, I think. And these are papers you can have a look. It's referenced in the paper somewhere in the conference proceedings. They produced around about 13 or more, I think, different varieties of models. So they went through a process of ascribing some taxonomy to it, all of which sounds a little arcane, but I want to talk about 4 of those. So the first of those, you've already seen it, the conceptual model. That's that mind's eye picture, or an Atkins sketch, as some people will refer to it, whatever it may be. It's where we develop those initial ideas of what it is that we're trying to do. We might follow that with what are termed learning models, and this is where we start to get the computer out and start to look at all or part of the systems we're dealing with, and hopefully start to test different configurations and different ideas. And I think a lot of what we refer to as analysis in an office is actually these learning models. But the important point is it's learning. You're developing your picture as you go of what it is that you're trying to design. Analytic models, in the way that David put it together, are a little different. And these are what we use to come along later and validate our problem. And so, for example, you saw Stu talking about that with the building where we came back and looked at it and agreed that, yes, it probably would get to 130%. No BS. And so these are the models we use later, not what we normally think of as analysis, but it's not too important. And finally, the next important model that we deal with as structural engineers are these blueprint models. And going back to that early picture of the Meccano set, that's the one which helps the builder put the whole thing together. Okay? This is all very simplistic, but it's quite useful to think of these things in this way because in the end, it's not actually about the engineering process, which is that finite little bit of work that we do on our desk to say we've done this wonderful thing. It's about what gets built that matters. One of the things we should avoid, though, is a prediction model. And why would that be? Well, because a prediction suggests that you know a hell of a lot more about what it is that you're designing at that point than perhaps what you do. I mean, in particular, the obvious thing is that the point you're designing it doesn't exist. It's a figment. It's not until it's actually built, until the contractor has made all the errors they need to, until you've missed all the things that you've missed and all those other things, that you've actually got the building that you've got. And so you can't predict how the building is going to perform. You can only put forward some ideas based on your analysis. And so we don't know enough to predict. And just as a bit of a salutary lesson, and a wee bit of an aside, I've carefully deleted names here, but some of you may know about this, but this is a large transportation project in Australia a few years back. Failed, as you can see there, after a year of operation at the cost of $1.7 billion to someone. And ultimately, the receiver sued the consultant. In this case, it was over forecasts or predictions, as the term was, of traffic usage. And the interesting thing was it all came back to a view of how the model worked. my understanding, and someone else may correct me on this later, but was that it went to court and the probably slightly too junior person who was presenting it agreed under questioning that the model was a bit rubbish actually, and so perhaps they shouldn't have used it in the way they did. But one of the things which subsequent commentators have come back with is that if they'd even taken the point of saying we use it as a learning model and then we use judgment to extrapolate the numbers that we were expecting, that would have been a much better defence. And I think the key thing, therefore, that was missing, and which we should always keep in mind, is judgment. And just to complete the horror story, you'll note there that settlement estimated in the region of 80 million. That's quite an expensive judgment error. So, to sum that up easily, we're not, or we shouldn't be, blindly led by our computing models, be they learning or analytic models. At the end of the day, the computer is just a tool. It only gives the answers, it doesn't ask the questions. And so we need to make sure that we're not blindly led by it, but we in fact do apply that judgment. So we test our understanding against our models, and we use those to inform our design decisions, not the other way around. And furthermore, if the computer model doesn't corroborate our conceptual model, something's wrong, but don't assume it's your concept that's wrong. Either the computer model is inaccurate, or maybe your conceptual model is inaccurate, but you still need to go back and think again about your understanding of what that structure was going to be. Why did you have those things in mind? What were you looking at? Because ultimately what we shouldn't do is just blindly assume that the computer has given us the answers to the right question. Oops, here we go. So once again, going back to my shameless plagiarism of David, I'd like to give you 3 principles which I gathered together from his papers, which I think are important. So the first one, requisite detail. There's a minimum level of detail that you have to ensure that you emulate the reality that you're trying to model. So in other words, you can't half do it. You've got to make sure you put enough in there that you'll actually get a meaningful answer, right? Very simplistic. The second, decision invariance. Don't keep piling the detail in. If you get to the point where the more detail you add, it makes no difference to the outcome, you've reached the point of stopping. And how many times have we gone back and looked at the most detailed models which have been produced by people? In fact, I think Paul referred to one earlier, where really the detailed model wasn't required because you were only testing one very simple concept. Final of the 3, and my favourite, the principle of consistent crudeness. I used to hear David use this term quite a lot without really understanding what he was meaning by it, but looking into it, there's really 2 parts to this, I think. First of all, no point in dwelling on the fine detail of one part of your model if you've got another part which you know nothing about. The second part, though, is identify the variables or the elements of the model that are going to have the most impact on the outcome and put most of your effort there because that's going to give you the better value for money. There's no point in spending a lot of time on the little details that don't matter. So, armed with those 3 principles, you can sum that up. Your model should be as simple as possible to tell you what you need to know and not so complex as to lose sight of the real issues. And I think, at risk of what I accused Paul of earlier, is going on the downhill slope from sort of the point of being the crusty old man telling people what to do, to fireside chats, whatever it may be. It's that whole thing about what do you tell people who are fresh out of university and come to work for you and looking at the computer and saying, great, let me loose. Well, I think these 3 particular principles would be a good starting point. Another couple of important things to think about are the roles of assumption and approximation. Going back to my earlier comment, you never know everything about something before it is built. And I'd almost go as far as to say we never know everything about it even after it's built. It's never practically possible to model everything. And so we have to think about how we're going to do enough that we can actually develop a design. And so we use assumptions and approximations. When we use assumptions, we've got 2 choices really. We can do something which is sufficiently conservative, we don't need to go back to it. And A great example of that, some of these assumptions, by the way, we don't even think of as assumptions, we think of them as gospel. A good example, though, the 95% characteristic yield stress that we assume with a reinforcing bar, right? We don't know what the strength of that reinforcing bar is going to be, but we choose an assumption which allows us to put it in there and leave it. We don't have to go back to that. We know that the wise people that put the building standards together have got enough leeway in there that it doesn't matter. The alternative is that we choose something which is sufficiently close to what we think it might be, put in a placeholder, and we can go back and verify that later. So a great example for most of us probably is what we assume about the ground conditions before we start building. And hopefully, though, after we've had a bit of good input from the geotechnical engineer, just to give them a plug, we don't forget them. But it's something that we look at and we think we may need to go back later, but we'll just put something in there now so we can actually move ahead. And it's really critical that we recognise which type of assumption we've made so that we do go back and verify those things later. And that applies to all aspects of our modelling. Approximations, on the other hand, we use for a whole lot simpler reasons. So we use that to limit the level of detail we're presenting. And so, for example, we might draw to LOD 300 on the drawings that we put out there. Something that we do because we know we don't need to show, for example, every purlin cleat for the builder to know that there's a purlin cleat required at the end of every purlin, hopefully. Another perhaps slightly more arcane thing there is that we also use approximations sometimes to convey the level of accuracy we're attempting to demonstrate. There's nothing more misleading than presenting that blue beam, fully detailed sketch of something which was a 5-minute concept. Perhaps it should be something which is in slightly thicker, blacker pencil on a scrap of paper. So in other words, let's think about the delivery to match what it is we're delivering. And so really to sum that up, it's important that our level of approximation is consistent with the level of information we're trying to impart. The key point that goes with that is whether it's an assumption or approximation, we need to test that sometimes with running a range of inputs, and so a sensitivity study. I think a lot of times, particularly for things like geotechnical parameters, we might plug a number in which is straight from the middle of a geotech report, but do we actually take the time to consider what would be the impact if it was a bit higher or a bit lower? And that can make a fundamental difference to what we're doing. It doesn't take much to consider that often, but sometimes that's a missing step, which makes all the difference, particularly when you do come back later and discover that, guess what, it wasn't quite what we thought. And so, back to our principles again, I'd say please remember the principle of consistent crudeness. Another point that comes up when we're looking at these models is this question of precision and accuracy. Not to be too choosy, but I think I heard that term used this morning and I thought, well, do we know the difference? And it's quite an interesting question because the difference is actually very, very important. Looking at that from down the sights, what does that mean? Well, as you can see, accurate and precise is pretty easy to measure, but when you start getting down to what happens if you're precise but not accurate, and you start missing the target, or neither accurate nor precise, they can be quite different. It's quite important sometimes that we think about that. Why does it matter? Well, first of all, false precision is a bit of a common trap because it fools people into thinking an answer is better than perhaps it is. As an aside here, those of you who attended the Earthquake Society conference earlier in the year, hopefully, as I got to hear Rob's wonderful Park and Paule presentation where he talked about this at some length and I think made some very good points. I wouldn't try and reproduce that, but certainly it was a very good discussion. And in particular, I think one of the ones that stayed with me from that was his discussion about how it is we present in remarkable accuracy sometimes the period of a building, which, when you think about it, is an exercise in approximation of the greatest order. We arbitrarily choose a level of damage which might accord to a certain ductility being attained, which maybe is at a certain point a secant stiffness out there, which might come back to a period, and it's probably on the fairly steep part of the curve. does it matter if we don't report that to 2 significant points? And so let's think about those. The second point there is accuracy is always critical, I think, but it's important that we think about the level of precision we require for a particular task. Quite frequently, people want to do things to the greatest nth degree, which really probably could sit quite happily in that chart there, and probably at a fraction of the time. And so how do we choose that level of accuracy? Precision, sorry. Is that something that we consciously think about, or is it something we walk into, being diluted a little bit, led by the nose by our computers? You want to be as precise as you can be, but you can't be more precise than the data you're working with. And again, it's amazing how many times people will use some very imprecise data to come up with some very precise numbers. Once again, whose fault? I think it's the driver. The last one is not quite so easy to understand. As you increase precision, it actually gets harder to be accurate. Now that sounds a little bit wrong, but hopefully I can illustrate that. So, is it possible? Well, there's your target. Without saying what we're aiming for there, if you're very precise, you could do that. Now, is that a hit or a miss? I don't know. It depends what you were trying to aim for. On the other hand, you could also do that, which is definitely a hit. And so, in other words, sometimes it's a lot easier to get a direct hit when you're trying to be actually relatively imprecise. And maybe that's all it requires. So without trying to say which you choose when, I think the important thing is to always think about that with special regard to what it is that you're doing. So looking at a couple of trivial examples. First one, and I've tried these, I might add in the office, to some interesting sorts of outcomes, so we'll see how we go. The steel portal frame, well, you could adopt a design guide solution. You can look up the dimensions of your portal frame somewhere and come up with an answer out of a cookbook, and perhaps design a bit of bracing by hand. You can use a 2D model, assume a few things and go for your life. Or, and I wouldn't recommend this, you could perhaps do a full 3-dimensional model with not necessarily E-tabs, but anything you like, using various different assumptions. Now the question is, I won't necessarily try and do this by a show of hands, I appreciate that it is just after lunch, but which is more accurate, precise, does it matter? So, actually perhaps I will try this. If you thought that, which do you think is the most accurate one? 1, anybody? Not very many. 2, anybody? Yeah, smattering of hands. 3? Almost no one wants to do 3, that's interesting. So I would put forward that if you'd said 1, give yourself a little clap on the back, because I reckon a lot of other people have gone to the trouble of verifying that those things are right, and therefore that might be the most accurate one. You haven't put yourself in the frame there, therefore you've probably got less opportunity to make a mistake. Someone's already checked it. But it doesn't really matter. The point is that you want to be thinking about this beforehand and choose the tool that's most appropriate for the job. Another example I come across quite frequently is this interesting old chestnut of do we use an ISA or a DSA for this particular building. And it gets more interesting still when you've got a DSA which is clearly a bit erroneous and someone's trying to get that remedied, and what do you have to do to prove that your new answer is in fact better. I choose this little building as a bit of a favourite from the old days, which is, I think the first number came in at 9%, and through talking it up a little bit we got to 18%, but it wasn't really until sitting down doing something fairly crude involving a scale rule in that picture to figure out that 54, which is in fact too precise, was actually closer to the number. But the point being that how do you come to these conclusions, and why is a DSA better than the ISA? Is it, as many seem to think, the weight of paper? Or is it the quality of thought that went into establishing why you might or might not think that this particular building is at that level of capacity? And the interesting thing being, I think, that when a lot of people get trapped into run the numbers, plug some things into a spreadsheet, come up with an answer, whereas the better thing to do might be to turn up to the building, have a look, poke your head under the floor, into the roof, all those sorts of things that you do to actually recognise what is going on with this particular building and highlight the particular vulnerabilities for this particular building, even if you then take a fairly crude approach and deliver up an ISA. So I think it's that whole thing about it's the quality of the thinking that matters, not the quality of the analysis. Another common question, I'm bouncing around a wee bit here, is this whole, when do we stop modelling? It is a bit of a joke and not always a funny one that, you know, what do we do in engineering? Well, we give someone a fee and tell them to keep on engineering till it's all used up and hopefully we're finished. And sometimes I think that temptation can be actually quite real. So the point here, when do you stop? Well, as I say, decision invariance, when you've got the answers you need, when you've validated your initial concept that you had in your mind, and when you've aligned your boundary assumptions. And that's quite a key point. Again, going back and doing that verification. And just to stick with the wise man routine, theory can be right or wrong. The model's got the third possibility, it might just be irrelevant. And so making sure that we have actually a match of our model to what we're supposed to be looking for is vitally important. Following that point through, one of the things that can drive me spare at times is this question: does the modelling drive the design process or the other way around? Now, slightly simplistically drawn example so it would fit on a page, but pretend, for example, we have a low-height shear wall structure. For the convenience of modelling, we tend to think of it as one of these, just the traditional lollipop bouncing backwards and forwards. But as soon as we made that assumption, going back to Paul's problem from this morning, we have to think how to tie it to the ground. And lo and behold, we end up with a whole lot of those. And so we can end up with a pretty big foundation structure. Fixed base leads to piles, leads to stiff structure, leads to low drifts, high seismic demands. Those things are not all bad necessarily, but that's certainly some of the outcomes you drive. If, on the other hand, you were to think of that a little differently and start to actually look at what's going on with the foundations, and it might be springs or it might be a non-linear rocking situation, maybe you'll find you don't need all those piles. And so how many times, though, have we ended up designing structures which have got very stiff foundations, not because they needed to have very stiff foundations, but because the model told us we needed to have that down there. And how bad is that? I might say at this point I did get someone pointing out to me that a rocking foundation system is, of course, an alternative solution, and that would lead us to another form of grief. But I think it's important we just keep the bigger picture in mind here that, look, we need to make sure that the model is the tool, not us. The computer doesn't tell us what to do. We ask it questions and hopefully it gives us good answers. And so the rocking base solution might lead to shallow foundations, which could lead to higher drifts but lower seismic demands. So long as we understand and recognise what the implications of that are, then we should hopefully be safe. What's the worst thing that we can do? I think I've heard this phrase used already this morning. It's to do something because we can. And I think that's the thing, that the difference between that 286 processor with 16K of RAM and 2 megabytes, in those days, because we can, didn't mean that much. But it meant that we did have to think very hard about what we were doing and not try and attempt the impossible, which is now a little more possible. And so I think the issue here is that computers and advanced analysis has enabled us to do stuff that we couldn't previously do. But the point I'd make to go with that is it doesn't make them any easier to build. And so if I look back that uncomfortably long period of time, I think back in those days, people were able to build things that we weren't even quite sure how to approach the design of. And so we had to use an awful lot of judgment to augment the small amount of computing capacity we had. Now, we can design things which can't be built. And, I hate to say it, people frequently do. So we've got to think very carefully how we use that newfound power we've got. And again, going back to an earlier theme, I think some of what gets shown to us at times by the architects, we might have these wonderful non-uniform curves and shapes which are now perfectly able to be designed using all the tools such as Rhino that we heard about earlier. And yet should we? Is that really a good outcome? we make those buildings horrendously expensive potentially, where sometimes by using a little bit of approximation, bring it back to that judgment we talked about, we could probably do something which looks 90% of the outcome for a good deal less effort and cost. So, a few points in summary. Key steps to success, perhaps. First of all, I think, know what success looks like. And that's been a bit of a theme, I guess, before lunch, talking to our clients, understanding what they want, perhaps understanding what their success factors are before we worry about our own too much, but hopefully using that to guide us towards what it is that's important at that level as well as in our models. Next point, always have a clear concept in mind. I still think that the most important model we've got is the conceptual model, the tool that we have in our heads all the time that allows us to be able to look at what we're producing and think, is that what it should be? Always understand the question before you look for the answer. Something I think I've said a few times is that there's many times I've seen engineers walking around clutching the perfect answer for the question which is never going to be asked. Don't be one of those. Be clear what you want from your model and drive it that way. And note, it's the engineer that drives the model, not the reverse. Always use the simplest form of model that can capture the problem. A, it's easiest to check. B, it's less likely to have something going wrong in it. And finally, please remember, someone may have to build it, so only do what can physically be done. And with that in mind, I'll leave you with Mr. Escher. Actually, it wasn't Mr. Escher, but it's a good cartoon.
Thank you very much, John. We've got time for a few questions, so if anyone's got something they'd like to ask. We are continually sort of getting asked by project partners and sometimes clients, but particularly project teams, to add ever-increasing levels of precision, especially into our BIM models and heading towards digitisation and digital twins. Do you have any comments around that drive to ever-increasing precision, given some of the comments you've already just recently made?
Fair challenge. I mean, I think the best tool we've got there is one word, really, which is why. A lot of the times people want stuff because they think they want it, and so it's really a matter of let's have a look into that and understand it. I don't think that's got to be an aggressive challenge. I think it's always got to be a matter of sitting with people and try to understand what's your motivating, what are you trying to do with this, why do you want that greater level of detail? Do you in fact need that greater level of detail, or are we talking about something else? You know, for example, in looking at a lot of cases I could think of, what they're really saying is, we think we could have a cost problem here, so can you possibly give me everything that I could possibly need so I can decide whether we really do have a cost problem? Where the real answer is, well, let's identify the things where the greatest cost uncertainty is and spend our effort on that, because that'll be where we get the most value for money, not in developing a more precise model or set of documents. Certainly at the other end of the scale, if they're using a BIM model or a digital twin for what it should be used for, then the answer is yes, you need to be accurate, but again, precision is perhaps why does it need to be that precise? We possibly still don't need to draw all the purlin cleats, just so you can do some maintenance on some of your systems, for example.
Great. Have we got anyone else with a question for John? Jeff Bird.
Great presentation, thank you, John. A loaded question. How can we embed some of this critical thinking at the design training level?
I'm going to, since we've got a bit of time, I'll wax lyrical at this point. I think we've got a bit of a challenge as a profession, which we need to think about, and it goes right back to core, really, because I think we've been branded with a certain brush which we shouldn't necessarily be accepting. Sorry, that was actually a bad mixed metaphor. We've been tarred with a certain brush which we shouldn't accept, perhaps. The problem we've got, I think, is we've been classified as a group of people who are purely technical. So we go through a process in early education of ramming people into STEM classes that we think might go there, and we then they fall victims of careers guidance at a certain point and get told because you were good at the STEM classes you go into engineering. If I think back over the years of some of the people I've had the most enjoyment and appreciation of working with, sculptors would sit as fairly high on the list. And that's for a couple of reasons, one of which is that they have by far the greatest understanding and knowledge, I think, of materials and behaviour of materials of all the people I've worked with. And second is because they challenge your creativity. And so my general view tends to be that if we can have engineers who don't have that great a grasp of maths, for example, because that is the stuff you can get out of the black box. But if they don't have creativity, they've got nothing. And so I think that the real issue is that we need to have those, we need to be pulling more people into engineering careers somewhere that have got creativity, imagination, and are not afraid to use it as being the better way of keeping the right challenges in front of people. So that's one thing. I think the training after that is a bit of a two-edged sword, because I know that there's been a lot of effort put into saying we need more soft skills in engineering, and that's true along the lines of communication, in particular of how to get ideas across. But we can't lose those foundation skills that we need around understanding the behaviour of structures and all the rest of it. I do think, though, that when we've spent so much time with what we can do on a screen and with the keyboard, as opposed to perhaps developing the craft at the other end, I'm just conscious that it would be great to do that. I'm sort of conscious, though, that puts me squarely in a Luddite territory, potentially, if you say, well, perhaps you're failing to understand how it is that young people learn these days. I don't think so, because I think the young people we see emerging from university are highly capable and able to do all the things that we need them to be able to do. They just perhaps haven't had quite that same opportunity to develop the feel and the craft of it before they get thrown into the deep end. Not sure if that answered the question, but it made me feel better.
And a question, might be a final question from Katie down the back.
Thanks, John. I had a question. I found your example about the steel portal frame really interesting. I said 2, I'm sorry. But I think the answer, your response that 1 might be the most accurate because it's been kind of road tested the most and kind of had the benefit of people doing it over and over again. I'm just wondering how we balance that with the challenge we were set this morning to think more like professionals rather than technicians and not do what's been done time and time before. How do we spot when it is good to do what's been done time and time before, or when it's good to push that, think a bit more outside the box?
Yeah, I guess that's where that judgment thing comes in. I think that the point that was made this morning was that there's a total, we do value the technician aspect of that as well. So it's really, the question isn't, do we want engineers with the ability to think back to first principles? It's a question of, we want them to understand when it's worthwhile doing it. And I think a lot of the things that I see that go wrong have been relatively simple things that probably could have been done properly in the first place at technician level, but it's usually the background of the thinking that didn't go into it was back at the other end, where it's developing that concept and so on. So I don't think, unfortunately, there's any sort of cookbook answer to when exactly to turn that on and go back to first principles and when not to. But I do think that people can be too quick to assume that we'll just jump into the black box approach to things, which is, by the way, no more, or no less, I should say, a technician-based approach, because you're still just plugging numbers and not necessarily having them go through the grey matter, which is the important part. I think, ultimately, if people can get the simple things out of the road, such as using the simple solution, then so much the better. I might add that I did get a fair bit of pushback on that one when I tried that internally. People suggesting that if we've got this tool which does all these things and allows us to come back and change it all again later if we need to because the client's changed their mind, why wouldn't we put it in the computer where we've got immediate access to do that? And so, there's arguments both ways. I'd say my response to that was, look, it was just an example, for goodness sake, but we need to let people use the tools they've got as best they can, but we just need to make sure that they're applying that judgment and that working at that level of understanding first.
Very good. Thank you, John. At that point, we'll again say thank you.